Hello, everyone. We're running a bit late, so I better get started. My name is Sascha Brunner. I'm chairing this session with Patricia Persaud today. And I'd like to remind you not to take any pictures of the presentations. And for the presenters, if you get asked questions, please repeat the questions so that everybody can hear. We have a big room, and people in the back won't hear the question otherwise. So I'll hand over to the first speaker today, which is Alexander Blanchette.
Well, good afternoon. I hope that you all have had a very nice lunch. I am going to be kicking off this session. I hope that you're all here to hear about mantle earthquakes and thin lithosphere. I'm happy to talk about it. You'll notice one of my collaborators, Walter Mooney, is listed here. He's going to be giving the talk after this based on data from a more expanded region of the same seismic array that we were using. And really what this work comes from is two remarkable observations. The first is that we have very thin lithosphere of only about 60 kilometers thick. And the second is that we have earthquakes within the mantle, which is very unusual. Here you can see my outline where in order to constrain the depth to the MOHO and to the lithosphere-asthenosphere boundary, I've used P-wave receiver functions. After that, I will go into this really unusual mantle seismicity that we observe. And then from that, we will move on to look at surface heat flow measurements along the Arabian Shield. And all of these things get fed into a thermal model for the evolution of the lithosphere beneath Herat Lunaire. And really, the bottom line here is that we use this to constrain the timing of thinning to have completed within about 12 million years of today. Here, I've just got a Google map image of Saudi Arabia with the Arabian Shield that stabilized around 540 million years ago. It's this large sort of bulge right here. And that was pretty inactive until about 30 million years ago when the Afar plume arrived. Shortly after that, there was initiation of extension within the Red Sea at about 25 million years ago. During this time, the Tethys Seaway was closing, and initiation of continent-continent subduction beneath the Zagros began at about 14 million years ago. And if we skip forward quite a bit of time, Herat Lunaire became active about 600,000 years ago. And this is where we're going to actually go ahead and take a look right along the passive margin here. On the left, I just have a blown up view of Herat Lunaire with our local seismic array. And I've gone ahead and right here is the dike that intruded within the crust in the year 2009. It came within about 1 to 2 kilometers of the surface. It did not erupt. There were about 30,000 earthquakes associated with it, and there's a whole lot of literature on that already. On the right is the source distribution for P-wave receiver functions. We have almost 10 years of data, over 800 earthquakes with very good azimuthal coverage. Those P-wave receiver functions were then common conversion points stacked within this black box around Herat Lunaire. And from that, we did this stacking in 3D. And so here I have one of my common conversion point cubes, as I like to call them. And each of these yellow lines is a slice through the cube where we're looking at different converters. We're looking at where are the velocity discontinuities. And so here I have a slice at about 38 kilometers that I've projected onto the face of the cube here. It's a red positive polarity converter. This is the MOHO. If we look a little bit deeper, down to 60 kilometers, we have the LAB, which is this blue converter. The reason we're able to see this on P-wave receiver functions is there's not a whole lot of sediments here, and the lithosphere, the mantle lid is very thin with respect to the thickness of the crust. So there's not very many crustal multiples getting in the way. If we go ahead and expand our view back to the seismic array around Herat Lunaire, there's one station over here off to the east named TRAS. This one will be very important in a little bit. The dike is still shown here. And this is here where we are in the Arabian Plate. And in calendar year 2014, there were about 6,000 crustal earthquakes down to a depth of about 20 kilometers, mostly confined here along the dike where they go from shallow to deep. During the exact same year, there were 65 earthquakes within the mantle, slightly disconnected by about 30 kilometers to the southeast of the tip of the dike. They line up on a plane with this strike and dip. And this disconnect becomes a lot more apparent in cross-section. So Up here, I just have distance along dip. This is as though you are to the east of the array, looking west. And on this next one, we're to the south, looking north. And so here are the mantle earthquakes that we've gone through great lengths to go ahead and relocate with a relative uncertainty of about 500 meters and an absolute uncertainty of about 2 kilometers, which is about the width of this plane. You'll notice that this seismicity is very much like a dike. There may be a little chamber over here. And then there's this aseismic zone that it looks almost as though you could connect the dots. But in this view, it's very clearly disconnected. There's a few earthquakes in this aseismic zone, but 6,000 versus 3. Another remarkable thing about these earthquakes is that they're not low frequency, they're not very low frequency, they're high frequency. Here we have one of the earthquakes at a depth of about 46 kilometers. I'll remind you the Moho's at only about 38 kilometers. And it's a very small earthquake, it's magnitude 1. And one of the things that's striking is it has very impulsive and clear P and S wave arrivals. This is the north component, the east component, and the vertical component. And on the spectrogram, they peaks at about 30 hertz for each one of these waves. It's very unusual. Here I've just gone ahead and we're looking at the depths of the earthquakes through time for calendar year 2014. This is all of the crustal seismicity, which very sharply cuts off at a depth of about 20 kilometers, more sort of traditional brittle ductile transition at about 350 degrees C. There's this aseismic zone, followed by the Moho, and then we have the mantle earthquakes here. And this isn't exclusive to 2014, as it turns out. In the catalog from 2010 to 2012, there are also these mantle earthquakes, and none of them go shallower than these or deeper than these. So we think that this is a very real mantle brittle ductile transition zone at about 850 degrees C. This number is a little bit elevated. It comes from the fact that we're in an area of higher strain rate from laboratory experiments on olivine-dominated rocks, as well as from the depth of nucleation of earthquakes beneath Iceland, where there are much stronger thermal constraints. For the longest time, we didn't realize that there was this surface heat flow measurement so close. This is going to be very important in our thermal model. Over here at site Yanbu number 1, there's an elevated surface heat flow measurement of about 50 plus or minus 4 milliwatts per meter squared. And we have an elevated mantle adiabat at about 1350 degrees C. These are the well-known surface heat flow measurements from the 1978 wide-angle refraction line. As you move from the center of the shield closer to the Red Sea, you can see that they gradually get more and more elevated. And the one from shot point 2 will be used as input, and the one from Yanbu number 1 we're just going to try to match. It's the closest measurement that we have. And here are just some geotherms that were derived from some xenoliths around the world, showing that this looks a lot like craton rejuvenation. This is a bit of a complicated figure, but I'm going to go ahead and walk you through this. At the top, we have surface heat flow. This is output from our model, where this is evolving throughout time. We calculate this at every time step. And this red line is the 50 milliwatts per meter squared that we're aiming for. Over here, I have the depth distribution of events as well as the 2 different brittle ductile transition zones, as well as the Moho and the LAB. And then this is the actual model run throughout time, where 0 time is defined as the time that the lithosphere stopped thinning. And so the way to read this is that whatever thermal state we're currently at, if we're here, that's how long ago in the past the lithosphere finished thinning. From the surface heat flow measurements alone, we have a constraint of about 9 to 14 million years. And we're going to sort of play this game of looking at these different brittle ductile transition zones to figure out how well we can tighten up this timing constraint. If we look at the shallow seismicity, one thing that I would remind you is that this is a bit of a squashed view. These are a lot flatter than they actually appear. And here's the 350 degrees C isotherm plus or minus 50 degrees. And this is just a reminder of the brittle ductile transition at this depth. This gives us a very broad range of time, starting from about 11 million years to beyond what the model run actually covers. So it doesn't, this makes sense because it takes a long time for the heat to diffuse from the lithosphere up to the crust. It's not as sensitive to the history that has occurred. Next, we're actually going to go ahead and look at the deeper mantle brittle ductile transition, where we have the 850 degrees C and then the plus or minus 50 as well, and a much broader range for the brittle ductile. This gives us a range of maybe 3 million years to about 14-ish. One of the things that you'll note here, I have the 600 degrees C isotherm, which is more typical of oceanic lithosphere. Had we used this, thinning would have completed about 3 million years ago, anywhere to practically yesterday, but we never would have matched the surface heat flow constraints nearby. So, can we line this up? Is there overlap between all of these thermal constraints? And of course there is, otherwise I wouldn't be up here talking to you about it. As it turns out, they all line up with about 12 million years ago in the past that thinning completed. The next question, obviously, is does this make sense? Well, one of our chairs actually proposed a model of two-stage rift evolution, where the top is an earlier stage where you have cold, thick lithosphere that is very strong and you have slow spreading. Below that, after you've heated up, if heating and thinning can outpace conductive cooling, you'll actually get the second stage that's much faster. It's kind of a runaway process. And this lines up with the geologic and tectonic history here, where 30 to 20 million years ago, we had rift orthogonal extension that should not be parallel. We have the older Herat volcanics and the rift parallel dikes, and we might have very broad domal uplift around this area. And then 15 to 20 million years ago, after the closing of the Tethys, initiation of the Dead Sea transform, and this change in plate motion, we have the rift oblique extension. There's the younger, more evolved Herat volcanics, and there's much more focused uplift as the uplift narrowed into the Red Sea Rift. So, I'm almost out of time, actually. I think this is a good point to just leave you with my conclusions and take questions.
I just have a question about the continental breakup of the Red Sea. Based on those thermal models and the model of extinction, what time do you think the Red Sea, the North Red Sea, is just a breakout, or do you think it's just still until today and no extinction?
So the question, if you couldn't hear, was based off of these thermal models, when will we do, I believe, the rift to drift transition instead of just mechanical extension? It seems that among rifts that have succeeded, it's about 10 million years beforehand, but I really can't answer that question at the moment.
We have time for one more quick question. Okay.
Well, I should be more correct in saying that thinning is very slow at this point. And the reason for that is we don't have very much uplift going on anymore. It's all gone ahead and moved more into the Red Sea. Beneath this area locally, it has either completed or very nearly completed. It's much slower at this point. We're not sensitive to that.
Okay, thank you very much. The next speaker is Walter Mooney.
This is here? Okay. So it's a great opportunity to tell you about our work on the Red Sea. The previous talk by Alex gave a great introduction to the topic. I'd like to emphasize, as he did, that the Arabian Plate is being pulled at the Zagros Mountains. That's the driving mechanism for the opening of the Red Sea. And you see the volcanics that begin at afar are on the east side of the Red Sea. So it's an asymmetrical rift. Now, when I talk to people about Saudi Arabia, most people are surprised to learn about the existence of the volcanism. And I have to admit, when I started, I didn't know either. The holy city of Medina is here, these big cinder cones. These are some big volcanics in the Herat Rahat. These are basaltic volcanics, so it's reasonable to suspect that the magma is coming from the mantle rather than the crust. So here's the standard kind of section across the Red Sea with incipient rifting. Shown here, thick lithosphere under Sudan. It's well known that the lithosphere is thinner in Arabia. There have been many studies. I have to admit that there are about 100 papers, and there's no way I can summarize the previous work, but there's been a lot of great work done in the Red Sea. And we do know that this asymmetry, we've long known that there's been this asymmetry. Now, Alex just showed you that from his receiver function measurements, he can nail the lithosphere-asthenosphere boundary at 60 kilometers here and the MOHO at 38. So now we begin to see the geometry of the study area. Now, the Saudis have put out a wonderful seismic array of broadband stations, Trillium T120s, and now they're up to about 200 instruments. And I'll show you today the results that we get from two-plane wave method seismic surface wave inversion for these blue stations. And I'd like to point out that there's an escarpment along the west side of the Arabian Plate. This is the rift shoulder. I'll refer to the rift shoulder later. So we have very good resolution, including, this is the Red Sea here, and here's the coastline. We have good resolution for different periods. 20 seconds, of course, is imaging the crust. 67 seconds is imaging down into the mantle. Well, I was really surprised when we looked at the VS in the crust, the 20-second surface wave tomography. We don't see any correlation with the volcanics. The volcanics, of course, are shown here in gray. So there really is no low shear wave velocity associated with the volcanic systems. The melt seems to be coming pretty much right out of the mantle, passing through the crust without a lot of alteration. And we get even the highest velocities, some of the highest velocities that we measure are along the Red Sea coast. In contrast, when we look at 66-second surface waves, now we're looking down at a depth of about 100 kilometers, we do see a very strong correlation with the volcanic centers. So this is the well-known low velocity zone that underlies western Saudi Arabia. If you wanted a summary of all the work that's been done in the past, the Yao et al. JGR paper that was just published contains all the citations that I'm unable to provide to you today in this short talk. So we see a really interesting pattern. So the magma seems to be associated with the Afar. That low velocity zone points right back to the Afar triangle. And now let's look at a cross section across the Red Sea. So this section is amazing, totally astounding. This is the Arabian Plate. That's the escarpment. This is the coastal plain, and there's the low velocity zone that's associated with those volcanic systems. And there's even a little break in the lithosphere. The blue is high shear wave velocity. And what we see is that the African continental lithosphere underlies the center of the Red Sea. So if you were to go out in a boat and do a deep drill hole through the spreading ridge, you would go into continental lithosphere. So our model for the Red Sea at 20 degrees north is that there's mantle flow, asthenospheric flow from the south. It's passing through a break in the lithosphere. The Zagros is pulling Arabia away from Sudan and Africa. And the Red Sea spreading center is being fed laterally. It's not vertical upwelling. It's absolutely astonishing. So this is the model in 3D. And you can see that the African lithosphere fits very conveniently back into the opening here. So what we have is a low-angle detachment fault, and the asymmetrical behavior of the volcanism is now very clearly understood as being a simple consequence of detachment fault opening of the Red Sea as shown here. Now, I just made the statement that if you look underneath the spreading center in the Red Sea, you'll find high velocity continental lithospheric mantle. And can I confirm that? As a matter of fact, if you look at any paper that's ever been published on the seismic structure of Arabia and North Africa, everyone has always found high velocities under the Red Sea, which they attributed to an error in their computer code. because you don't expect to have a high velocity. So this is the cross-section that's 20 degrees north, under the Red Sea. Kulikov found a high P-wave velocity. He's using P-wave tomography, so you get streaking. I don't have time to go into the limitations of each method. But you see, even in 2015, Kulikov was saying that the Red Sea is underlain by high velocity. So you have a high velocity under a mid-ocean spreading center. That's, by the way, not textbook geology. If you do not expect the unexpected, you will not find it, said Heraclitus 2,500 years ago. So expect the unexpected and maybe you'll see it. So this is what happened. As Alex just pointed out, between 9,000 and 12,000 years ago, the thinning was finished underneath Rahat, and then a low-angle detachment fault developed, and the Red Sea began to open at 20 degrees north. And this is the geometry. You know, this is a cartoon, but actually this cartoon is exactly the same as the image that we get from seismology. So it's a cartoon based on facts. And so this is the geometry at 20 degrees north. So this African lithosphere fits back into the opening here, except for the part that's thinning. And you have the volcanism is coming up through that upwelling. Now, if we go to 23 degrees north, we move out of the Red Sea trough into another zone of the Red Sea. The Red Sea turns out to be pretty complicated. And we get this image. This is, again, S-wave velocity. The well-known low velocity zone underneath the escarpment and the elevated region is here. And we have more continuous high velocity lithosphere as shown here. So our interpretation of that is that we don't have seafloor spreading at 23 degree north. What we have is just pure continental extension on a detachment fault. If you are patient and wait another few million years, this is going to continue to, well, actually, Arabia is going to continue to be pulled away, and you'll begin to get a normal geometry of a spreading system. So this is what it looked like. If you close, all I've done is taken the tomographic model and closed the Red Sea. So again, although this is a cartoon, it's actually a cartoon based on the data. And this is the pre-rift structure. So before Red Sea extension at about 12 million years ago, this is what the geometry looked like, and this is the part that Alex was saying had been, the thinning had occurred between 9 and 12 million years. So when you teach your classes about spreading centers, I'm sure that you use a diagram very much like this. Unfortunately, you're not telling the truth if you tell them that's what the Red Sea looks like, because it doesn't. The African plate is actually underneath the spreading center. It's being fed from the side, and the whole thing started out on a low-angle detachment fault. Well, I've discovered that I've never done anything original in my entire life, that everything is derived, was already predicted by people much smarter than me. And 32 years ago, Brian Wernicke published this well-known paper in the Canadian Journal of Earth Sciences where he showed simple shear. He forgot to put the volcanism over here, but we'll forgive him for that. And this is basically the Wernicke model for the Red Sea. Now, there was a German fellow who was in Canada in 1985, and he went back to Germany to teach at the University of Karlsruhe, Hützel. And he told his PhD student, Folgenritter, to use the Wernicke model to make a low-angle detachment origin for the Red Sea system. And An Yin told me about this paper. I had already gotten our model for the Red Sea, and I hadn't read this paper. And sure enough, back in 1985, I think that should be 88, sorry about the date, they proposed the model that I'm talking to you about today. At that time, they believed, though, that the Red Sea had evolved further than it actually has. So in summary, what we're finding is that depending on what latitude you're at, you have a different kind of structure in the Red Sea. But the interesting one, in my view, is this one here, which is a really great example of low-angle detachment faulting producing a new ocean basin. Thank you very much. Lots of time for questions, because I still have 2 minutes left. Plus, maybe there's also, anyway, any questions? Yeah, I've been looking into that, and I haven't found it yet. And this may be unique. You have to catch it just at the right time. Yes, and another question back there.
To speak about asymmetric or symmetric structures, we have to have equal resolution on both sides of the HC. Do you have any planning to cover the other side of the...
Thank you. Oh. Can we go back? So, our colleagues in Egypt have a marvelous seismic network. And I plan to go to Cairo in February and ask for ask for the data in Egypt. And for Sudan, we're looking for volunteers to go to Sudan to deploy seismic stations. So you can meet me after the talk to sign up.
One last question, Thilo.
Do you have a mechanism for the initiation of a low-angle model?
Well, the mechanism, the Wernicke paper is pretty clear about that. I mean, the simple shear detachment model. It's really it's a natural consequence of how faults develop in an Andersonian world. It's favorable geometry.
Wouldn't it be normally much steeper?
Much steeper.
Yeah, like they normally fall much steeper. You would need a stress rotation or another mechanism.
Yeah.
Low angle.
I would say I'm probably not qualified sufficiently. I haven't looked at enough detachment faults in the basin and range and elsewhere to give an adequate answer. But I should.
We have to move on to the next
work
speaker.
harder.
Thank you.
Thank you.
Okay, hi everyone. So I'm Aude Lavayssiere, and I'm going to go a bit south of the Red Sea, imaging the lithosphere beneath northern East African Rift. So the region I'm looking at is this region over here that started rifting with the separation of Africa and Arabia 30 million years ago. And then there was a separation from the Nubian plate and the Somalian plate around 11 million years ago that created the main Ethiopian rift, and then the triple junction with the Red Sea rift and the Gulf of Aden. And this region is really interesting because it exposed the transition from the continental breakup in the main Ethiopian rift all the way to the seafloor spreading in the Red Sea. So it's like kind of a spatial and temporal evolution of continental rifting. And so the objective of the study and what I'm going to talk here in this talk is understanding the behavior of the lithosphere during continental rifting. And if I'm talking about lithosphere, I'm going to talk about the lithosphere-asthenosphere boundary, or LAB. So there's been lots of definition of what is the LAB exactly. So the transition from the rigid plate to the asthenosphere. It's a difference in strain rate, in temperature, in anisotropy, and all of those definitions doesn't always correlate to the same depths. So in this talk and in this study, I'm only talking about the seismic contrast between lithosphere and asthenosphere. So I'm looking for a velocity decreasing with depth. So for this study, I used everything I could find in northern East African Rift, so 182 stations coming from a number of projects like the Eagle project or the IRIS database, and some temporary network in Eritrea, Yemen, and Djibouti. And so all of these gave me around 16,000 waveforms to analyze. So for those of you who don't know receiver function, this method is really useful to know the structure of the Earth beneath each station, and particularly to locate the velocity discontinuity. So for this study, it's mainly the MOHO and the lithosphere-asthenosphere boundary. But it's also really useful in this method because we can potentially locate the melt zones. And you're going to see that in East Africa, it's really useful. So I'm looking at the conversion from an S wave. It doesn't show. never mind. It's change in S wave to a P wave at a discontinuity. So from the 16,000 waveform I had, I manually picked all of those and then did some quality control, which gave me around 3,700 waveform to analyze. So I've filtered them and then migrate them all to depth using a local velocity model. I've also used waveform modeling for having an idea of the velocity changes through the lithosphere. So what I did is using a stack of the waveform in 3 representative bins from the Ethiopian plateau, the Afar, and the main Ethiopian rift. And I do a synthetic forward modeling, which means I create a 1D velocity model, and then I calculate the receiver function associated with this model. So that's the red line, and then I compare it to the data. And what is important to remember is that I'm not looking at the absolute shear wave velocity, I'm looking at the velocity changes. So coming back to S2P receiver function, that's usually we show them as cross section, so that's what I'm going to do now. And it's a red, white, blue picture with blue feature meaning velocity decrease with depth, and red feature velocity increases with depth. So in this region across the MER over here, we have 2 main features, a red feature here that I interpreted as a moho. And you can see that over here, beneath the MER and extended beneath the plateau, the signal is really complex. It's really thick compared to the rest of the moho. So I'm going to talk about it later. And the second feature is this blue feature over here that I interpreted as the LAB. Thank you. And what is really interesting is that it actually disappears when we go beneath the MER and the Rift Valley. So if we go across Afar, again we have the moho that sends, that shallows into the rift. But this time we have only a small signal of the LAB over here beneath the Somalian plateau, but it disappears again beneath the rift. And if we go along the rift, we don't have any signal or really small signal of the LAB, so we have no LAB beneath the plateau, beneath the rift. But we have a nice moho that shallows as we go towards the Red Sea, so towards the seafloor spreading. So the idea next was to look at each interfaces separately. So for the moho, I looked at the moho depth, and it's interesting. We have 27 kilometer moho beneath the main Ethiopian rift that then shallows as we go toward the Afar depression to around 18 kilometers. And we have really interesting moho beneath the plateau, quite complex. We have zone where it's quite shallow and zone when it's deeper. So it goes to 30 to 27 kilometers. So I'm going to look at this zone that correlates to the cross-section I was showing before. So that's this complex moho with really thick signal. And it's interesting because it actually correlates with the presence of volcanic activity. And it also correlates with where other studies have found high velocity layers. So what we think it is actually lower crustal intrusion. And the S2P receiver function actually show a lower crustal intrusion and moho as the same interface. So that's why we have this thick red blob. But going to the lithosphere-asthenosphere boundary, what was really striking is the difference in amplitude between beneath the plateaus and inside the rift. You can see that as we go next to the rift, the amplitude drastically changed. So the idea that came up was, does that mean that the LAB is weak, or does that mean that the LAB is not here? So in terms of depth, we only took result as strong amplitude, which gave a LAB at around 66 kilometers between the plateaus. But what is interesting is actually that this low amplitude LAB correlates with volcanic activity and with the slower shear velocity. So in 2016, Gallagher et al. found those lower velocities that came up in pink over here, that correlates quite nicely with my low amplitude LAB. And what they found is that there is partial melt in the mantle. And if we think there's partial melt in the mantle, that it means there's no more seismic contrast between an asthenosphere full of melt and a lithosphere full of melt too. So that explains why we can't see the LAB in the S2P receiver function. It's also interesting, but less. It's a bit tenuous, but with the waveform modeling, if we look at Ethiopian plateau, we see the LAB quite nicely with the velocity decreasing with depth. If we go in the main Ethiopian wave, we have no velocity decreasing with depth, but we have a velocity increasing at around 90 kilometers. So that's this one. So that's really small. So we can't really say for sure it's here, but the depth correlates nicely with what Ferguson and other petrologists have found as the onset of melting. So it should be good. We have melt production at depth and then melt percolation through the lithosphere. But the problem is with a 1D velocity model, a lateral variation is also possible to create that kind of thing. So we would need more testing to be sure. If we go a bit global, we have a moho thinning nicely as we go towards the seafloor spreading in AFA. And then we have a strong LAB signal here, but we have melt percolation in AFA and the main Ethiopian reef that actually masks the velocity contrast because we have loads of melt. So in conclusion, we have now a large-scale, high-resolution images of the lithosphere in the northern East African rift. We have a moho discontinuity image across the whole region with the crust thinning towards the Red Sea rift and some lower coastal intrusion. And we have the lithosphere heavily deformed by melt infiltration with no LAB signal at all beneath the rift, which give evidence for melt in the mountain. Thank you for your attention.
We have time for questions.
Do you have any handle on how much melt would be needed to actually mask the LAB? What are we talking? Maybe just maybe percent melt to actually.
So I can't answer with a receiver function. This Gallagher et al. Found that less than 1% would be enough to create the slower shear velocity. But for my study, it's too complicated and would need way more testing.
Other questions? John?
Why do you say that the LAB is being masked by melt? Is it not being stretched away and it's just not there?
It's two possibilities, I guess. It's either, when I say there's partial melt, we can't really say the lithosphere is really here because it's not rigid anymore. So I can't say that the lithosphere is here or not here. I say there's partial melt, so I can't say it's here. It's the only thing. And so I still can't say that it's completely thin away, but it's also possible.
Okay, one last question, Stefan, and the next speaker can come up, please.
One more comment. So I think you are right. So probably something is going on there. So if you have information process ongoing, you will not get LAB just because your angles are changing. So you will get LLB if you have contrast, which is quite positive. If it is distorted over, so you get a kind of deformation process of filling lithosphere. Then you will lose it.
Sorry, I'm not sure I understand exactly what you said. Can you just?
It's not flat. It's not flat.
It's not flat, yes, but it's true that if the LAB is completely tilted, then the S2P wouldn't show up, but it does show up in the plateau. So it would mean it's really steep, going from the plateau at 66 to more than 50 degrees to disappear.
Thank you very much.
The slope across all of
Yeah.
I think we have to postpone the discussion for later. Thank you. So the next speaker is Sarah Jaye Oliva.
Good afternoon, everyone. I'll be talking about state of stress in magmatic rift zones, specifically in East Africa. So what are we interested in? We know that sills which are bedding parallel intrusions, dikes are bedding perpendicular intrusions, and magmatic intrusions accommodate strain, but only one of these actually usually reach the surface and would be easy to study. Yet we know that sills exist. So here in this study, we probe further how the processes involved in sill complexes. So these are stretching processes and magma-related processes at once, and a sill complex would accommodate strain in rift and provide shallower magma source for dike intrusions, and usually this would also be accompanied by faulting. And if those faults are sold to the sills, then it could be used as a conduit by magmatic fluids to escape. And to study these, the East African Rift is a good place, specifically Tanzania. So this would be, that's East Africa, and Tanzania is right here, but I'm specifically interested in an area right over here where there was a dike intrusion in 2007. This occurred between two volcanoes, Oldonyo Lengai and Galai, only one of which is active, the famous Lengai. And the series of events are shown down here, where in July 2007, an earthquake swarm began, coincident with diking, and also the diking was here in the flanks of Galai. And also there was a effusive activity in Lengai, which later transitioned to ash eruptions. So it seems here that there's some source of stress triggering occurring between the diking and the earthquakes and the eruption. Now, here again, just for reference, this is Oldonyo Lengai, Galai, and that's where the diking was. So the dike was in 2007. In 2013, the crafty Colibria array of 39 broadband seismometers were deployed around the region. So that's the blue triangles over there. And that has allowed us to study further in detail that region. There was also an array out during the time of the 2007 diking. That's the red triangles down here, but they were all to the south. And just for reference, I will also be mentioning this station later on. This is KMBO. It's the nearest permanent station, and it's in Nairobi. So this is an image of a compilation of stress direction indicators in the region as published in our paper just this year, Weinstein et al. The beach balls are summed focal mechanisms. The black ones are from teleseismic earthquakes compiled for this small region here since 1964 to 2007, up until the dike intrusion in 2007. And this red one is the summed focal mechanisms from the local array as recorded by crafty Colibria in 2013 to 2014. Both of them agree and show roughly north-northwest extension, while other seismicity studies in the north in the Magadi Basin, that's Yves Bonset et al. In 2001, and also to the south in the Manyara Basin, that's Albrecht et al. 2014, reveal extension that's roughly east-southeast, right there. And relative plate motion from GPS studies, shown here in the red arrows, reveal roughly east-west extension. And so we observe this local stress rotation in this small region, which is also an area of interest between these two volcanoes, revealing a rotation of about 60 degrees, suggesting that there's a local stress field here dominating over the regional stress field. And Ooh, that's a different color. But, okay, so this is a cross-section, and again, this is the area that we're interested in. These are the two volcanoes. It's Oldonyo Lengai and Gelai right there, and then the diking in 2007 occurred right there. And we imaged and interpreted a sill complex in this region from gravity seismic joint tomography by Recker et al., and that's this image shown here, and seismicity patterns from Weinstein et al. So this is where we I think the sill complex is, and it's being sourced from this magma body. And the 2007 dike probably was sourced from this sill complex located right here. Now, this is a focal mechanism of the largest earthquake in 2007 that accompanied the diking. And it matches very well with two earthquakes that we recorded in the Crafty Array in 2013, right over here. Now, it's a bit off to the side, but we have to remember that we're in a region of the Earth where permanent stations are sparse. So the locations here we found could be up to 20 kilometers off. So based on just similarities of those focal mechanisms, we think that that earthquake could have occurred right at the sill complex. We've also done waveform modeling for moment tensor inversion. These are the two earthquakes mentioned in the previous slide. And those are also the two earthquakes that we're most interested in. And we find that at least 4 of these 5 earthquakes have strongly non-double couple components. So this is a source type plot where double couple, which is your sliding on a planar fault, plots here in the middle, your isotropic plots in the top and the bottom, which is your volume change, and CLVD, your compensated linear vector dipole, plots on either side, which means that any deformation is compensated in the opposite direction, perpendicular to it in the opposite direction. And we see here results from bootstrapping for at least for these 2 events. Bootstrapping shows that the source mechanism is robust and not quite double couple. And this could be interpreted as fluid involved. And this goes back to this, to the idea of if a fault is soling to a magma chamber or a sill, it could be used as a conduit for gases, thus creating a non-double couple component in the earthquake. But there were only a few earthquakes recorded by this network, so we wanted to look at other earthquakes, figure out if this was related to the 2007 earthquake. So what we did was look at KMBO, which was the permanent station in Nairobi, bandpass filtered the waveforms to the same frequencies used for moment tensor inversion, and found out that yes, a lot of the earthquakes from 2007 matched the 2013 earthquakes, and also found other two earthquakes in that time period that matched 90% correlation in the vertical and 80% on the horizontal, which is pretty good. These are the earthquakes. They're roughly all over the area, but again, in this area of the world, the location errors can be a bit larger, so we think that they're actually happening in a smaller region and driven by the same mechanism. Now, we also pointed out earlier that it seems that there was a local stress field dominating over the regional stress field. So here we present some 2D physics-based models of the area as we prepare for doing 3D modeling work that I didn't quite get to for this presentation. So these are just a list of the modeling setup and where we're getting the data. We constrain our models using data and results from the region. Topographies from SRTM30. Basin depths are constrained from refraction and wide-angle reflection studies up in the Magadi Basin, and also inverse models from gravity and aeromagnetic data. The depths of the Moho and the Conrad discontinuity are constrained from receiver functions and tomography results, which all come from the same data set, the Crafty Colibria data set. And we do the analytical model by modeling the topography as a line load in elastic 2D half space using equations from Torsten Damm 2000. And we also add, in addition to the topography, we add the far field extensional tectonic force, which even though tectonic forces we know are huge, for this one we're only adding a 10 megapascal perturbation, which is roughly the global median stress drop. And we then model the principal stress directions, where sigma 3 can be taken as a likely opening direction for a sheet intrusion. And if we visualize it that way, we can then take sigma 1, sigma 2 to be where the sheet intrusion would be, or the direction where the sheet intrusion might propagate. So we take sigma 1 as a proxy to figure out the preferred direction for an intrusion. So here's some of the results. These are east-west cross-sections going from north to south. The first row is the topography, and there's the basin. The second row shows sigma 1, which again is the preferred propagation direction, where red is horizontal sigma 1, so something that would support sills and magma storage. And yellow is vertical sigma 1, which would be diking or volcanism. The third row shows stress magnitudes, where red is least compressive or extensional. And then the bottom row shows a tomographic map from Recker et al. So these are shear wave velocities, where red is low velocity. And we see here in figure 1, this is in the northern part of the Menatron Basin, and the topography is mainly just the rift topography. And this creates a magma storage, a preferred magma storage area right beneath the rift here, and off-rift magmatism, where we have more of the yellow spots off-rift. And here in the second figure, we have a volcano on the rift. So there's a volcanic edifice, this is Galay, overlain on the rift topography, and that narrows, this stress gradient narrows this zone to a smaller region. And then even further south, this is the cross-section right in our area of interest, with the two volcanoes, Oldunulengay and Galay, next to each other on top of the rift topography. This topography then concentrates the stress gradients, focuses the stress gradient even more to a narrower region. And coincidentally, this agrees with the observed magmatism and the tomographic results, where this region of where there's yellow right next to red, this region of yellow-orange is where the 2007 diking occurred, and right next to it here, where there's red, is where the sill complex is. And this lower part here is where the tomographically imaged magma chamber seems to be. And so just in summary, we've observed a local stress field due to a sill complex that dominates the regional stress field, as observed from seismicity, focal mechanisms, and GPS. Non-double earthquakes could be due to fluid involvement and intrusions, again, when the fault is soling to the being a conduit for magmatic fluids. Multiple regional earthquakes occur in the same location over time could be due to repeating mechanisms and a persistent subsurface structure, and the rift topography encourages volcanism and also focuses the stress gradient when there's two volcanoes next to each other. And the future work will be 3D modeling of stress rotation. Thank you.
We have time for questions. Yes.
You have a low velocity zone and interpreted magma chamber very shallow in the crust. So the volcanism is rhyolitic?
I did not interpret that. Okay. You're referring to these ones?
Well, another figure you had labeled there, magma body.
These ones, yeah. I don't.
Well, what's the composition of the volcanics?
Very low silica. So the volcano is carbonatitic, but it has some other lavas, but still low silica lavas.
So that doesn't look right.
Any other questions?
We can talk later.
I would have one. What kind of changes would you expect if you go to 3D instead of 2D stress modeling?
I'm actually curious to see how that would work out, because everything from the dikes to the earthquakes seem to be showing this stress rotation, but a sill would be radial. So I think it has something to do with the topography of the volcanoes being next to each other, but offset quite a little bit, that would create the local stress field.
Okay, thank you very much. Then we move on to the next speaker.
Hi, I'd like to thank the conveners for giving me the opportunity to tell you about some recent work we've been doing constraining basin scale structure in the Malawi Rift from 3D refraction imaging. And I'd also like to thank all of my collaborators on this work. Oh, I'm changing the wrong. Sorry. Great. And so we're moving further south in the East African Rift system, and I just wanted to give us a brief overview of the characteristics of the western and eastern branches. I'm showing topography on the left, and then a comparison of volcanism and seismicity on the right between the western and eastern rifts. And what I'd like you to take away here are the differences between the two. You all probably know that the eastern branch is much more abundant volcanism, while the western branch has isolated locations of volcanism and abundant seismicity as well as deep seismicity. This abundant and deep seismicity is one indicator of very strong lithosphere, as well as high values of effective elastic thickness. Also, one of the main characteristics of the Western Rift, if you look at the topography of it, is these narrow and long rift valleys that are along the western edge of the Tanzanian craton. And these rift valleys are made up of long rift basins that are filled by very deep rift lakes. And we'll be focusing on the Malawi Rift here, which is at the very southernmost segment of the Western Rift. And the Malawi Rift is a unique location along the Western Rift. We sit here south of the Tanzanian craton. Volcanism is limited to the Rungwe volcanic province in the north here. This rift has these very characteristic asymmetric basins where we have the North Basin right here. This is a half graben that's bounded to the east by the Livingston Fault, which is a west-dipping fault. We step south into the Central Basin here, which now we have the Usisia Fault on the west, which is an east-dipping array of faults there. And I'm showing the border fault traces in red and intrabasin faults in yellow here. The Malawi Rift is a weakly extended rift, and extension rates right now are thought to be relatively slow. And so I'm showing here a schematic of what these basins look like after Ebinger et al. 1999, and also what they look like in cross-section. And I wanted to give a brief overview of the motivation for this talk. So a long history surrounds the controls on the development and ultimately abandonment of long border faults like those characteristic of the Western Rift. We know that there are very characteristic relationships between geometric parameters like fault displacement and fault length, as well as lithospheric strength and the influences of surface processes. We know that these faults accommodate significant amount of extension, especially in the earliest stages of rifting, but competing models for normal fault growth have different relationships between parameters like displacement and length, and very few data points exist for faults of such great length like here in the Malawi Rift. And it's important to understand the relationships and geometric scale of these faults, because this has important implications for both seismic hazard as well as the mechanics of how continents rift apart. And so I'm using offshore data that was a part of the multidisciplinary segment project. This was the study of extension and magmatism in Malawi and Tanzania. This included geochemical, geodetic, and active and passive source seismic. And I'm just listing all of the US scientists as well as African and other international collaborators and institutions without whom this project would never have been possible. And I'm going to focus on the active source experiment. This was done in spring of 2015, and I'm showing here the experiment geometry where the red circles show an array of 32 lake bottom seismometers. These are some of the only lake bottom seismometers that had ever been deployed at the time. And the yellow lines show the track lines of where we shot air gun sources in the lake. I'm showing an image of the deployment of lake bottom seismometers here, as well as the modified cargo ship that we used to tow the source, as well as a 1.5 kilometer streamer. And I wanted to show you just a little bit of this data. It's a unique data set that's very non-2D, very 3D, I would say. I'm showing here a receiver gather that I've outlined here in turquoise that was recorded on this instrument here, 121, just showing excellent ray coverage across the entire north and central basins. We have a lot of crossing lines, which allows us to pick very consistent first arrivals here. And so we picked over 100,000 first arrivals on the 32 instruments, and we invert these using the FAST methodology of Zelt and Barton for a 3D VP model. We apply a Monte Carlo approach where we invert 200 unique starting models so that we can have direct access to uncertainty, as well as minimize the influence of starting model on the final product. And I'm showing here a depth slice that's 4 kilometers. I'm showing the VP model, percent uncertainty, and ray coverage. Note I cut the color scale here at 20 just to highlight regions where we had lower ray coverage, but in fact we have more than 100 rays in almost all parts of the model. What you'll see in this depth slice is you see green colors, which are representative of crystalline basement, and then turquoise to bluer colors that are representative of sediments. And you'll see that the blue colors are trailing against the Livingston Fault to the east here in the North Basin. They then smoothly transition to westward dipping sediments, or westward thickening sediments, against the Usisia Fault here in the Central Basin. And you'll note that we see really nice correlation between the locations of mapped intrabasin faults from reflection imaging and where these sediments are bounded within the basins. And so now I'm going to step through different slices through this model. Again, I'm going to show the location of the slice on the left, along with the border fault trace and intrabasin fault traces. And so right now we're sitting in the north. We have the Livingston Fault to our right here, and you see a very thick pile of sediments against it, very little sediment on the west-hand side of the basin. As we step further south, we start to see these very prominent intrabasin structures here. Again, these have been mapped in reflection imaging, some of them to have significant offset on them, and we now have more than 3 kilometers of sediment against the Livingston Fault. As we step further south, closer to the transition zone, here's where we start to have our thickest pile of sediments, close to 5 kilometers, again, all thickening against the Livingston Fault. Now we've stepped into the central basin here. We still see a significant amount of sediment against the tail end of the Livingston Fault here, but we begin to see the implications of the Usisia Fault. And as we step further south, we now no longer see such thick sediments to the east. We see thickening of sediments to the west against the Usisia Fault, and we see a very prominent intrabasinal horst, again mapped from reflection imaging, that bounds a lot of this sediment in the central basin. And now we've stepped the furthest south. We have the Usisia Fault again, significant piles of sediment, and again thinning towards the east, showing the prominent influence of the border fault here. And so one of the main objectives was to map syn-rift sediment distribution to get at fault displacement profiles. So we've defined a contour that's representative of the base of syn-rift sediment. We did this because our velocity model does not have interfaces. So we use co-located reflection lines to identify what velocity contour is the best. We picked 3.75 as it lies in the middle of this very high gradient of velocity between sediment and crystalline basement. And I'm showing a map of 3D sediment distribution here on the right. Note we have the thickest amount of sediment in the North Basin along the southernmost segment of the Livingston Fault here, where there's greatest bathymetry in the North Basin. And then we have greatest sediment in the Central Basin against the central segment of the Hissisia Fault, again where we have a significantly deep bathymetry. And so now what I've done is I've combined these estimates of sediment thickness against the two border faults with estimates of the elevation of the footwall escarpment onshore. So let me walk you through this plot. We have estimates of the elevation of the footwall escarpment on the top. The black line is our final elevation model. The gray line, if you can see it, was the original elevation profile, where we've now removed anomalously low elevations due to erosional features. I then combine that with these estimates for the thickness of syn-rift sediment along the two border faults, and I've highlighted our velocity contour of 3.75 and the thick blue line, which is the one that we think is best representative of this. And then we combine the estimates of the footwall escarpment and the depth to syn-rift sediment, and then we get at this estimate for vertical offset along the two faults. And so 3 things I wanted to highlight. One, we see thick sediment in the accommodation zone. It's sort of shown here by where I've put fault tip overlap. Over 4 kilometers of sediment is sitting in the accommodation zone, and we think that this may be an indication of the early establishment of fault tip lengths in the accommodation zone. Other authors that have studied the Western Rift have shown evidence for the early establishment of fault length, and so we think that's consistent there. In our estimate for the total vertical offset of these faults, we find that both faults reach total vertical offsets of slightly over 6 kilometers there. And so now we'll assume a fault dip of 60 degrees. This is consistent with focal mechanisms as well as onshore mapping and reflection imaging. And we place these faults now in a global context. So here I'm showing a global normal fault distribution on a log-log plot of fault displacement versus fault length. And here are our faults quite all the way up here. I told you there's not a lot of data points for faults of such great length. And now I show you this is no longer a log-log plot, but now I'm comparing the results from this study with results from other studies. Note that for the Baikal Rift and the Kivu Rift, I've used estimates for a basin length, so these could shift left or right a little bit. And what we find is that while our faults plot within the global trend, when we compare these to models for the maximum amount of fault displacement, like the one proposed by Oliva and Ben for the East African Rift system, they find that faults should only reach about a maximum displacement of about 5 kilometers here, and clearly we are well above that estimate. And so this points you to questions like, have we begun migrating strain inwards, or have these faults been abandoned? And I think further study, especially from the seismicity studies that are ongoing, will really help nail down, are these faults still active? And so I'll leave you just with the conclusions and also my favorite slice through our 3D model, which is in a long strike slice from the North Basin through the accommodation zone into the Central Basin. And just point out again, we've found over 7 kilometers of displacement for these two faults, 4 kilometers of sediment in the accommodation zone, and that both faults have quite a bit of displacement, potentially pointing to a soon migration of strain inwards. Thank you.
Any questions?
Estella. So it's not the greatest in the accommodation zone. It is about 4 kilometers in the accommodation zone, and then we have 5 kilometers of sediment against the, let me show you. So you'll see, I mean, the color scale gets a little close once you get to 4 kilometers, but we do have more sediment in the against the central segment of the Lavayssiere fault and against the southern segment of the Livingston fault. There are two very large rivers that pour, or at least one large river that pours into the accommodation zone. So that could also be leading to the significant sediment there.
Other questions? If not, then thank you again, and we move on to the next speaker.
Hello everyone, my name is Annika. I'm postdoc at JUMSTEC in Japan, but I'm actually going to talk about some results of an undergrad research project I conducted as a student at Victoria University of Wellington a couple of years ago. And it's going to focus on a gravity study from the central volcanic region in New Zealand, quite a long way from what we just heard before. And this region is also often referred to as the Taupo Rift or the Taupo Volcanic Zone. The gravity study conducted at the time had the primary aim to validate the interpretations of a crustal seismic experiment. And I would thus in particular like to thank all those that have previously worked and published in the area, because without all the constraints and interpretations that we've got from other people, we wouldn't be able to produce any gravity modeling. Now, looking at the geological setting, the central volcanic region is a back-arc rift system that formed by spreading behind the Hikurangi margin, which is the plate boundary between the Pacific and the Australian plate just off the east coast of the North Island. And this subduction back-arc rift system continues for thousands of kilometers into the Pacific region along the Kermadec-Lower Harbour system. The central volcanic region thus provides the opportunity to study the southernmost extent of this rift system in a continental setting. But what's the most interesting factor about this area is that it's not only dominated by very, very voluminous and primarily rhyolitic volcanism, it has also an extremely high heat flux that's on par with the Icelandic hotspot and can be measured along a whole lot of discretely spaced geothermal fields in the area. Now, just looking at the gravity signature displayed here is the Bouguer anomaly interpolated over the central North Island, and you can see that it's dominated by some very high wavelength and high amplitude gravity signatures of the subduction zone over the east coast and the transition from continental to oceanic lithosphere along the coastlines. However, removing these broad regional fields leaves a residual field that's dominated by a roughly triangular area of low gravity fields, which on its eastern margin coincides with what is often referred to the Taupo volcanic zone. And you can see in this area there's some areas of extremely low gravity which coincide with the rhyolitic calderas that have been active over the last 1.6 million years. However, the field does extend a little, the gravity low does extend a little bit further to the west. At its northern end, it extends into the older Hauraki rift system, and the western margin is also dissected into a number of what we think subparallel basin structures, and it's still up to further interpretation what actually caused this kind of dissection. Early reconstructions of the plate boundary zone throughout the North Island suggest that it has been dominated by strike slip in accordance with the propagation of the Hikurangi margin throughout time. And one idea is that it could actually reflect on this early strike slip dominance during the onset of rifting in the area. Now, the main crustal structure constraints I'm going to use is the latest of a sequence of exploration seismic surveys conducted. The so-called Menlo crust experiment was conducted by Victoria University of Wellington in 2005, published a couple of years later, with the aim to resolve mid and lower crustal structure in the area. It was conducted along a 140-kilometer long line that roughly crosses the southern end of this rift structure. And while I'm not going to talk about the seismic data in detail, I'd just like to outline the main features. So the interpretation of the authors is that of a roughly 25 kilometer thick crust beneath the rift system that features an upper crustal rift basin of up to 2.5 kilometer depth that is infilled by low seismic velocity and possibly low density volcanic clastic sediments. And it also features a subcrustal rift pillow that's up to 10 kilometers thick. Now, assuming that the gravity signature we observe on the surface is that from upper and lower crustal features, what do we expect to see in such a setting? The figure I'm showing here is that, the model I'm showing here is that of a 2.5 kilometer deep rift basin that's isostatically exactly compensated by rift pillow at depth. And what you can see in the green line there, apologize, I do not have a laser pointer. What we can see in the green line there, you see that the gravity signature of the rift basin on its own would be that of a relatively short wavelength but high amplitude gravity low. However, its combination with the long wavelength effect of the high density structure in the lower crust would result in that of an either even shorter wavelength gravity low that is flanked by some gravity highs. But what you can also see that if we produce a model that ignores the structures in the lower crust, we would significantly underestimate the total gravity effect of the low density bodies in the upper and possibly mid crust. Now, what I'm displaying here are the topography grids and gravity anomalies extracted from a line that roughly coincides with the transect of the crustal seismic experiment I talked about before. And looking at the gravity data here, you see this characteristic rift type gravity low in an area that spans about 70 kilometers that's flanked by some prominent gravity highs, especially here on the eastern margin. It's up to 10 milligal high, which is very interesting because this gravity low high actually lies on top of a plateau that's known to consist of downfaulted basement rock that's overlain by about 500 to 1,000 meters of low density volcanoclastic sediment. So based on that, we cannot interpret the gravity signature of the rift system based on upper crustal features on its own. The final model I produced here, you see the observations in these big black dots and the calculations on the slide, consists that is exactly based on the geometry of the interpretation of the seismic data, and it features this upper crustal rift basin for which we adopted a layered medium where the density increases from about minus 600 kilogram per cubic meter down to minus 200, which reflects on the lithostatic compression of the infill in the basin, which has also been seen in borehole data. What's an important implication of the low density contrast at depth means that the lower boundary of this rift basin is very, very poorly constrained based on gravity data on its own, and we could actually, based on the gravity data, extend it further. For the subcrustal rift pillar, we adopted a density contrast of 300 kilogram per cubic meter, which if we assume a standard crustal background density of around 2,700, would consist of mafic rocks such as, for example, a gabbro, which is also consistent with the P-wave velocities of around 7 kilometers per second that we've got from the seismic data. Now, during the initial gravity modeling, we left the mid-crustal structure open for later interpretation. Now, assuming that our rift pillar in the lower crust essentially acts as a driving force for subsidence and downfaulting in the upper rift basin, we would assume that our gravity model should be roughly isostatically compensated over the rift axis. And to achieve isostatic equilibrium, we needed to adopt a small density contrast of minus 110 kilogram per cubic meter. And the question is now, what effects would lead to this density contrast beneath the rift axis? First of all, given the high heat flux within the central volcanic region, we would assume that there's an elevated geothermal gradient within the mid-crust. However, our calculations showed that an elevated geothermal gradient on its own cannot fully explain the lower densities observed. So we also calculated and suggested that there's possibly up to 10% of isolated melt intrusions or low-density rhyolative intrusive bodies in the mid-crust, which coincides well with the interpretations of previous studies conducted, for example, using magnetotelluric data or shear wave velocity inversions that suggested the presence of melt bodies or rhyolative intrusives in this area. You can see that no perfect fit has been matched in some areas in the model. However, these areas coincide to some small regional anomalies. What's also noteworthy here is why we assumed isostatic compensation over the rift axis. You can see that the margins are uncompensated, and we're suggesting that in these areas the forces are supported by lithospheric strength, which coincides to some form of regional compensation mechanism. Our overall crustal thickness has been decreased from 25 kilometers to around 13, which would lead to a stretching factor around 2. However, assuming that there's about 10% of intrusive bodies within the mid-crust, we could say that the stretching factor would be around 2.3. So there's some assumption leading to that. So to just quickly summarize, it is a small study. However, it could be shown that based on the gravity data, the interpretation of seismic experiments that were conducted in New Zealand can be validated or might be correct. And the results also confirm interpretations from previous authors that there might be melt intrusions or low-density rhyolitic bodies within the mid-crust, which then implies that the high heat flux observed within the central volcanic region might be caused by such effects. I think that the gravity field observed also is a very good example, textbook example of a gravity field over an active rift basin, including deep structures caused by subduction and then features in the upper and lower crust. Thank you very much.
We have a lot of time for questions.
We can go back to your model, gravity model, the density model. Yeah, I was wondering if the high density material plus 3 kilograms per cubic meter were intruding the crust, wouldn't the crust become denser rather than lighter? You have the middle crust having lower density, but if it were intruded with a high density material, it would raise the density.
Well, there's separate interpretations to it. I mean, one of the interpretations that people have brought forward is that we actually have some form of differentiation prospect, which would explain why the volcanism up in the central volcanic region is primarily rhyolitic, which would then imply we get low density material in the mid-crust.
Thank you.
Other questions? If not, then thanks for the speaker.
Thank you very
and
much.
we take 2 minutes break before we start with the next speaker. Natalie, do you happen to have the laser pointer still? No.
Actually, the gal who was speaking, she had given it to the tech guy. He took it outside. That's why she lost it. The tech guy took it out, actually, when she couldn't use it. So I think it's the same. No. Yeah, sorry. So, the next slide. And you can use the up and down.
thanks for waiting. We continue now with Alyssa.
Good afternoon. I'm going to take you to a different continent again and talk to you about the Rio Grande Rift. And we're going to actually focus on much more shallow crustal signatures of rifting than we have been so far in this session. So hopefully that'll be fun. The Rio Grande Rift is in the southwestern United States, and it's a north-south oriented rift, essentially about 100 kilometers long, and goes through the entire state of New Mexico all the way up to central and potentially northern Colorado. Some people think Wyoming, but that's highly debated. And the rift itself is sandwiched between these two very undeformed geologic provinces. So we have the Great Plains to the east, which are low relief, undeformed region, versus the Colorado Plateau to the west, which is a high elevation, relatively low deformed region. And sort of, as of now, the idea that rift-related extension and magmatism sort of began in the late Oligocene. It's pretty great to study the Rio Grande Rift because it is a rift that's visible all across land, so you don't have to try to do any subsurface underwater imaging or anything. And there's also a lot of data. It's an easy place to get to, so there's a really high volume of data in the region. But even with that much data, there's still a pretty big debate on the evolution of the rift. And that sort of debate centers around two simple ideas, one being, did extension and magmatism happen synchronously across the entire rift, the length of the rift? Or was it more of a northward propagation where you have extension beginning in the south, moving through to the central part and up to the northern part of the rift, kind of like a zipper? And so I'm going to try to answer or get at conclusions about these debates by looking at shallow crustal processes and looking at low temperature thermochronology. So here we have the rift, and I'll reorient you. I've put north now to your left, so everybody can get a nice good neck stretch for the next few minutes. I'm going to show you images of the rift in this orientation for a while now. And what I think is that these simple ideas of either synchronous initiation or northward propagation are a little bit too simplistic, and that in fact there are three different distinct segments in the Rio Grande Rift. And so these segments are really defined by both the structure, the spatial orientation of the structures, and the magmatism in the region. So the northern Rio Grande Rift I define as this section with the red box around it, and you can see that the major faults associated with this part of the rift are very long north-south striking normal faults that bound asymmetric basins, and that there's one really large single fault system for each latitude, each basin. And then you can see that in this green volcanism here is actually pre-rifting volcanism. This is early Cenozoic before rifting begins. And then as we move into the central part of the rift, we have a really big change in our orientation. Our faults are now northeast to southwest, and they're dominated by left lateral strike slip motion. You also have a lot of these really small north-south faults that span the entire basin. They don't have very much vertical offset, but they are normal faults. And here you see that the volcanism is quite a bit different. It's really, really young, high-volume volcanism in that central part of the rift. And as we move to the southern part of the rift, we move back to large fault systems, again, north-south orientation. But this time, at a given latitude, there are several basins, large fault systems, creating really wide basins. In the magmatism here, you can see that there's that old green-colored volcanism, pre-rift volcanism, and then a few sparse deposits of really young quaternary volcanism. So I think that there's a lot more to say than just this rift has evolved, either at one specific time or through time in a specific way. And so I want to bring us back to the question of, is there a temporal evolution seen in this? And are these three segments that we see related to some sort of temporal evolution? And again, the way I'm going to look at that is through low temperature thermochronometry and taking that data and doing inverse thermal modeling. Really quickly, for those of you who aren't familiar with low temperature thermochronometry, the chronometers I'm going to be talking about are apatite helium, apatite fission track, and zircon helium. And these are chronometers that focus on the really lowest of the low temperature thermochronometry systems. So we're looking at temperatures less than 250 degrees C, so fairly shallow crust. And what's great about these different chronometers is that we can look at information on timing of exhumation, magnitudes of exhumation, and even in rates. And the way we can do this in a rift system specifically is by sampling several samples with a vertical spatial relationship that we know. And so here I have sort of a schematic diagram of your normal fault here, and your footwall has been exhumed up during fault activity. And so these stars are sort of your schematic vertical sampling transect. And so you can see that as the samples move from deep at high temperatures through those zones that the thermochronometers pay attention to, they record a cooling age for the samples. And as those samples move through that and then get exposed to the surface, we can see the timing for when that's happening and how fast it's happening. So you get a sort of generalized cooling history for those rocks. And so that vertical part of the graph there shows you that that's when the fault is really active and exhuming the rocks quickly to the surface. So what I've done for this study is gone to the northern part of the rift and added a lot of new data. This is a region where there's extensive data sets throughout, especially the central and southern part of the rift, but the northern part was lacking. And so we've now filled in this gap here with new apatite and zircon helium thermochronometry. And then I've added some apatite and helium zircon throughout the rest of the rift to sort of expand that temperature range that we're looking at. And so with these new data, I can compile that with everything that's already been collected, and now you have this very large data set with over 400 samples of thermochronometric data across the entire part of the rift. So this color scheme here is just showing you the cooling ages of those samples. So to go through some of the trends we see in this northern part where we're close to Wyoming, this is the region that is sort of still up to debate on whether or not it's really part of the Rio Grande Rift. You can see that at least the thermochronometric ages are still really quite old. There isn't any young, significant exhumation seen in that northern part. If we go to the section that I've called the northern part of the Rio Grande Rift, you can see that along the footwalls of all of these fault systems, you're starting to see these really young ages, less than 20 million-year-old ages, really dominated by 10 to 5 million-year-old ages, especially in these northern sections here. When you move to the central part of the rift, we go back to seeing a lot of these really older ages on the footwalls of our faults here. And so we don't see a lot of high magnitude extension in the central part. Whereas we go back to the south, and you can see again on the footwalls of all of these fault systems, you're getting those younger ages. So that's great. We have a really good idea of a very generalized cooling history for part of the Rio Grande Rift. But we want to get at specific timing, magnitudes, and rates of this movement along these faults. And as I said, the way we do that is collect several samples along a vertical transect. And then from there, we can put them into a thermal model. So this is an example of an inverse thermal model. So you take the data from the vertical transects and put it through this program. I've used a program called QTQT, which inverts the samples. And what's really useful about this specific program is that you can put several samples that have several different thermochronometers, thermochronometric data in them, into the same model, and sort of model them together as one large package of rock that's moving in the same relative sense along the fault. So with a graph like this, you can identify your timing for when rates of change are happening, and then you can also convert your temperatures to relative depths. And that's essentially just using a generalized geothermal gradient. And so from there you can sort of make estimates about how much rock you're exhuming and how fast it's happening. So here I've identified places throughout that whole data set where we can put together many samples that have a vertical relationship that we know about, and think of them as vertical transects, and then model them and come out with results like the model I just showed you. And so these different transects are all throughout the entire rift, and generally what we see is that in the northern part of the rift, you have the onset of exhumation beginning between 25 and 15 million years ago. Magnitudes of exhumation range from 4 to 6 kilometers. And again, I just want to point out that there is no young volcanism in this northern part of the rift. Moving to the central, onset of exhumation happens prior to 50 MA. So all of the exhumation that occurred in this central region happened during the Laramide orogeny, not during Rio Grande rifting. And so the magnitudes of exhumation that have happened in the late Cenozoic are less than about 1 kilometer, since that's what we can detect with our low temperature thermochronometers. And again, pointing you out that the young volcanism is ubiquitous in this part of the rift. And then as we move to the south, we see similar signature to the north, where you have onset of exhumation from 25 to 15 MA, magnitudes of exhumation that are about 2 to 4 kilometers, although that's pretty large, but it's still not as large as in the north. And then again, this post 25 million year old volcanism is really sparse throughout this region. So from this data, my preliminary interpretations, again going back to that question of whether we had synchronous initiation or if there was a northward propagation, is that the rifting signature is not really, between these 3 segments, does not seem to be caused by temporal evolution from the south to the north, and that it's much more synchronous in terms of fault activation and magmatism. And that maybe the spatial variability between these 3 segments is actually potentially related to crustal and lithospheric characteristics. And this idea comes from, very simply, the fact that your lithosphere-asthenosphere boundary changes dramatically across the rift, right? So you can see that in the north, where we have our discrete, large, single fault systems with our largest magnitudes of exhumation and young thermochrometric ages, we have a fairly thick lithosphere, on the order of 80, 90, over 100 kilometers thick. And then when you go to the central part, you can see that, or remember that there's a lot of strike slip faulting, and that the exhumation is not very large magnitude, and so that potentially this extension along this region is mostly accommodated by magmatism. And this magmatism, if you remember, is sort of centralized right here, which happens to be at a very abrupt step in our lithospheric thickness. We're going from lithosphere thicknesses over 100 kilometers and then over a very short spatial distance, getting to thicknesses that are 60 kilometers. So it seems like those volcanics are centered right on a really abrupt change in our lithosphere-asthenosphere boundary. And then when we move to the south, you have the large fault systems, but they're diffuse throughout that whole region, making it a really wide rift signal. And then we have large magnitude exhumation, and again, not as great magnitude as in the north, but we maintain this thin lithosphere. So I'm just going to summarize from this data. I think low temperature thermochronometry is really useful for looking at things like the timing of exhumation along large fault systems. And we've been able to fill in some of the gaps that were in the data set for the Rio Grande Rift, as well as expand the temperature space that we were exploring before. And through this, I think there are 3 different styles of rift accommodation that you can see throughout the Rio Grande Rift. And it points a little bit more towards synchronous initiation along the Rio Grande Rift, and that a lot of the spatial relationships we see may be, in fact, due to lithospheric properties. Thank you.
Questions?
What are your thoughts on the possibility of small-scale convection in that central segment?
The question was, what are my thoughts on the possibility of small-scale convection in that region where we saw the volcanism and the big step in the lithosphere-asthenosphere boundary? And I think there's a very good case for that, because that boundary and that quick step happens between the Colorado Plateau and the Rio Grande Rift, but it also happens farther west between the Colorado Plateau and the Basin of Range, both in the south and the north, and it's the same really quick transition and really high volume quaternary volcanism. So I think that maybe edge-driven convection might be some factor here. Yeah.
Other questions? Yeah, in the back.
Do you have different geothermal gradient for the north, central, and southern portions? Can you model it?
I have. The difference in the geothermal gradient based on heat flow is less than 10 degrees, and the thermal models that come out of changing your geothermal gradient by less than 10 degrees do not show any big significant changes, but I've done models for all of those scenarios.